Okay, so today we have a group of 7 of us. Okay, again, I'm happy to see the all the stars, and we have Evan, our regular. We have James Ling, and we have David, and we have Alex. Alex is hiding himself, and then we have Evan. Evan started the last time, so today he will finish his old problem left from the last show. And let me start with the what? The geo problem we have been dragging on for a while, right? It started with Ivan's Amy problem, and then we went on to a simpler geometry problem with that structure, and then we link it to the IMO 1997 P2, and then we were linking it for the next show is the 2008 USMO P2, right? So now let's talk about this one. Um, I'm going to use this diagram I have. Oh, Ivan, you want to show us the problem, or I will show the problem? What do you want me to do? I can show the problem.
I think if you show the diagram and people who, yeah, we need to explain the condition.
Yeah. So this is the diagram, right?
Yes, I believe you have triangle ABC. You pick any point U on that small arc BC, right?
Yeah.
And then we draw two perpendicular bisectors until we intersect AU in 2 points,
Yeah.
W and V. And then BV and CW intersect in point T. Do you guys see this?
Yes.
So what
and then we want to prove what? We want to prove this AU is equal to what? BT plus what? CT, right? So guys, if you like geometry, you should really go back to what we did last section, and about talking about that more special structure is about the tangency. And this problem, we remove the tangency away. With the tangency, I think you guys should follow what James talked about. That harmonic quadrilateral, that in line to me too, because at the beginning I didn't see that too, and as soon as James said that, I know immediately everything becomes very, very clear and trivial, right? So of course it's not trivial, because only harmonic quadrilateral, then it becomes very, very nice. So this one I want to talk about, it is the structure is very similar, and we take away the what, the perpendicular, the tangent thing, but the angle are still the same, these two pairs of angles. So this is where I say this problem becomes very linked to the solution I explained to you guys last time. Is how do I make these angles make more sense? Is I have to kind of like use the arcs, because this angle right now is bad. This angle is good. They are facing BU. And this angle is kind of like nowhere right now. So we are doing the same thing as we did last time. If you look at this picture, angles is how do we use these angles to the arc, right? So last time we talked about is to extend these lines, because then naturally we are talking about arcs now. So what we are having is here, right? So based on this, you can see the problem becomes very similar. This problem and the problem I talked about. So these two are equal. So that means this arc is equal to this arc. So we start to see lots of what? Isosceles trapezoids. And this angle and this angle are equal. So now we know, if we use the color, then we know this part will be equal to what? This thing. So in this way, now this problem basically becomes what we talked about last time, because now you should see two direct isosceles trapezoid, but also because they are the same, together you have the third what? Isosceles trapezoid. So if you look at a better picture, is like this, right?
Zooming, can we have some also points?
Yes.
So we can have a connection.
Label them again. So A,
yes.
B, C, and this is U, and this is V, this is W, this is T, right? See, my wife works at a company called TUV. I suddenly realized this problem uses exactly those letters, T and U and V. Suddenly it becomes very, very familiar to me. Okay, so I call this B1 and I call this C1.
Because I'm trying to understand how you can use, you constructed two arcs, how do you use that AB1 arc nicely?
AB1 arc is BU arc, right?
Yeah.
So now I have an isosceles trapezoid here.
So AU, I know what is AU right now. AU
Right.
is equal to, do you guys see what is AU?
See, now AU is very good. I basically remove AU to what? To BB1, right?
Yeah.
Right? And because the problem is symmetry, you also know AU is CC1. Either one is fine now, because now I start to land those segments. Originally, I want to prove AU is equal to what?
BT plus CT.
BT plus CT. But AU, by my picture, is already equal to BB1. And the BB1 is equal to BT plus what? B1T. So now my goal is to prove this one now.
Okay.
Right? So that's clearly true because CT and the BT1, now, like I said, you have two isosceles trapezoid. Actually, you have three, right? Because the third isosceles trapezoid is hidden because the big two arcs are the same, right? So if you connect the B1, C1, you are basically done, right? Because that's the third isosceles trapezoid. So B1T should equal to what? CT. Right? Because that's the where they intersect here, right?
And this is IMO problem in 3 minutes, right?
This is IMO problem just by just drawing the picture, yeah, right? But the original proof is not hard too. They did some angle chasing around here. It will work out anyway, right? But I think this one is really nice. Is now you see the whole picture, right? Okay, so you guys can go back home online for the audience is to check out 2008 USMOP2 because I made that problem really under pressure. We were missing geometry questions, so I have to find something to generate one. Now you can see the structure is very special. I just make this line passing some special points.
If you're missing geometry, it's fine, right? You just have one geometry instead of two. It's great.
Yeah.
You're giving them the wrong impression of how USMO problem selection happens.
I mean, this isn't the first time, right? Yeah. I heard somewhere that the 1999 AHSME had to be completely reworked because it got leaked out somewhere. Which is, or I don't know if it was 99. It was one of the 90s exams. Yeah. And also IMO 2015. So this stuff happens all the time.
But IMO 2015. When I was traveling, I realized the problem got changed as a coordinator. They're sending me, I got informed, right? But now I think Evan is doing a much better job. He has a great packet because we have wonderful returning students contributing, and he's checking out all those things. And I think right now we are not in short of any questions. But I think we are still in short of simple questions. We have lots of hard questions that I cannot solve on the package. I think that's clearly true, right? That's clearly true. Yeah. Okay, so I'm going to leave the floor to Evan, right? Evan, you go.
I think we can do a little more, another problem first.
Okay.
That algebra problem.
Oh, that algebra problem. Yes, David's question. Yes. Yeah. That problem, I'm very happy because I know how to do it.
I thought we weren't telling the problem authors and they're making them guess.
Well,
it's fine.
Maybe
we can have a different poll, right?
Oh, where is the problem from?
Yes.
You should only make them guess if James proposes the problem.
Okay. So guys, you can read the problem. If you are quick enough, you can post your answer to our panelists. And yeah.
When I read this problem, the first reaction is I thought that the problem was like has a typo. I was looking for x squared plus 1 over x squared. Then I realized, oh no, it's not a typo. It was intentional.
That's basically the entire story of how this problem was made. If I'm being
because
perfectly
x squared
honest.
plus 1 over x squared, you see it in every math counts practice, right?
Yeah.
I'm actually going to talk about that a little more in a little bit, but let me just screen share as usual. Oh, can you enable participant screen sharing?
1 sec. Yes, I can. All panelists. Yes. Now you should be able to see.
It's good now, though. I need to check. Give me a sec.
No rush. Our attendees can find the answer.
Oh, thanks.
All right. For some reason, it just like I would be. Can you see my screen?
Yeah.
Okay. For some reason, like usually it has me like screen share only a part of the thing, but oh well. Anyway, so what is this problem? We know that x plus 1 over x is equal to the square root of 22, and we want to find. Let me put that over here. So want to find x squared minus 1 over x squared. Okay, so as Zooming has noted, there are lots of problems of this type, and many of them you see over and over and over again. I'll present 2 examples. The first example is the case where you're given x plus 1 over x, and you want to find x squared. Okay, let me rewrite this. So the first example is given x plus 1 over x, find x squared plus 1 over x squared. And this is a super common problem because it's like the prototypical definition. It's like basically the prototypical example of a good, easy math contest problem because the solution is super short. In particular, most of us probably know what's going on here. You can square this. If I take this square, then the AB terms are going to cancel out, quote unquote, and we're going to be left with an integer. So if I'm given this term, I can compute this term by just subtracting 2. Okay. So that's the first example. The second example, if you're maybe a little more adventurous, you might see the following problem. If instead you're given x minus 1 over x, find x squared plus 1 over x squared. And this is slightly less common, but it's also pretty common because if you notice, the trick is exactly the same. Because fortunately for us, the squaring trick still works. It just so happens that now we have a -2 instead of a +2. This ends up not being an issue at all. Okay, so this problem, if I remember correctly, was basically inspired by just swapping the plus and the minus sign in that second example and seeing what would happen. Now, you may be thinking, oh, well, that's a really arbitrary change. Why would you ever even think of doing this? It turns out this has been done before. Not this exact problem, but there, just as an aside, there's an old Caltech Harvey Mudd problem from 2012 or something like that that says given xy equals 8, minimize x squared plus y squared over x minus y, and assuming that x and y are greater than 0. And I've always viewed this problem as sort of taking a standard case where the minus sign is on the top and the plus sign is on the bottom, and just reversing it and see what happens. I don't know. This problem's always stuck out to me like that, and I think that was sort of in my head when I was thinking of this version. So there you go. It actually turns out that the way you solve this, the Caltech Harvey Mudd problem, and the way you solve this problem are basically exactly the same. Anyway, so we don't know. So let's go back to our example. We don't know how to compute. Unfortunately, the squaring trick doesn't work anymore, right? As Zooming noted, the squaring trick completely fails because when we square a negative number, we get a positive number, right? So now when we try to square x plus 1 over x and x minus 1 over x, nothing works anymore, and we're sad. But we're not that sad, because we do have another. What's another tool we have at our disposal?
You can solve for x itself.
Yes, you can. And admittedly,
this
that's why this problem is a number 2, right? Because we put this problem so early on this exam. So this is 2018 CMIMC algebra number 2. And the reason we put it as a number 2 is because we knew contestants could just solve for x. And so there's no point in making that problem hard when this hack is there, and it will work if you can catch it.
It's not even a hack, because
it's not even a hack. Yeah, exactly.
There's some shortcuts you can take too.
Yeah,
all
exactly.
Right, continue.
I mean, the problem is almost equivalent to solving for x, right? Because
I agree.
it's easy to find x squared plus 1 over x squared. So you just need to e over x squared.
I mean, once you find x, you find x minus 1 over x, right?
Yeah, that's where I'm going. That's where I'm going.
All right, sorry, continue. My bad.
So we know what this is, right? We know we have the tool we have at our disposal is called difference of perfect squares, right? So if we can find x plus 1 over x, we have x plus 1 over x. So if we can find x minus 1 over x, and we're done. So one way we can find x minus 1 over x is literally solving for x. But the way that I framed this discussion, the nice way, quote unquote, is staring at you already on this board. What's going on? What's the nice method? I'll give you a hint. How do those two expressions relate to each other?
Well, they differ by 4.
Yep, exactly.
Yeah.
So that's the no bash way to do this problem. And those of you who know me on AOPS know that I'm very anti-bash, even though this is not really a bash, but still. The point is, there's another relationship. And as an aside, this is essentially the same thing as the relationship a plus b squared equals a minus b squared plus 4ab. It's the exact same thing. But the point is, now, once you know what this is, you can solve for this. So 22 equals x minus 1 over x squared plus 4. And the stipulation that x is greater than 1 implies that this thing is positive, because then x is greater than 1 over x. So if you solve this, you get x minus 1 over x is equal to the square root of 18. Or 3 root 2 if you want to simplify things. And now we're basically done, because if you push that all the way up here, this is equal to root 22 times 3 root 2, which you can simplify to be 6 root 11.
Makes sense.
Okay, good.
So, yeah. This problem was on the exact same exam as the last problem that I showed. This one was number 2, the other one was number 8. So, make of that what you will.
So this was a warm-up, right?
Right?
Yeah.
Yeah, so this was a warm-up. I think we can move on to something difficult that we started last time, and Evan had an interesting intro. USA GMO, quite recent, 2016, right, Evan?
Yeah, 2016.
2016.
So let's see if I can figure out.
Yeah, thank you, David. It's a cool, nice problem. We need more like those for computation.
I mean, not all problems have to be hard.
Yes, we need all levels. We have audience, right? Everybody can learn a little thing.
Okay, so as a reminder, here's the problem statement I'll put up on the left. Yeah, and last time as I got as far as writing down a bunch of powers of 5, so I guess I can start by doing that again for the people that weren't there last time. All right, let's see how fast I can compute this. So this guy's 25, this guy's 125, there's a 6125. And since the problem is asking about zeros, we're going to kind of be paying attention to those. 75, yeah, well, 78125. And the first zero that you see is going to take place at this 5 to the 8th step where you have 390625. But it's not so much that particular digit 0 that I'm interested in, but in fact this entire substring at the end. So this whole thing, this 0625, that 65 is something that should look familiar to you. It's like the 65 from a few rows before. Now for concreteness, do I want to push out more of these? Well, okay. Maybe since I went all the way up to 5 to the 16th last time, I'm not going to keep pushing it. But my idea is, okay, well, I have the 0625 that appears. Question, can I get 0625 to appear at the end again? Because if so, then I have a reliable source of at least a single digit 0. And well, what's happening here is if I want the number to be 0625, can I assume the audience knows what a mod is?
I think so.
Think so? Okay. All right. So what we have is, if I'm looking at the end, what this is saying is I want 5 to the 8th to be 0 mod, 5 to the 8th to be congruent to 0625 mod 10,000. And if you've done any sort of these find the last so and so many digits, what you know is that eventually the numbers should always repeat. And so it's simply a question of how long is it going to take me until I get to the next repetition. Font size is a little small. So mod 10,000 is a very big number, which makes it hard to think about. So what I'm going to do is I'm going to split this 10,000 into two things. It's 2 to the 4th times 5 to the 4th. So we are almost always fine modulo 5 to the 4. Like this number, I keep throwing 5s at it, so the number will always be divisible by 5 to the 4. So by the Chinese remainder theorem, if I want to get back to 065, all I have to do is take care mod 16. So the question is, if 5 to the 8 is whatever 065 is mod 16, how long does it take until I get all the way back? And if you know what the Euler phi function is, you can use that, but I'm going to be a little, at least for the time being, I'm going to be a little sloppier and say, well, there's only 16 numbers, so is there a way I can do this? Is it worse to bring up the Euler phi function or to bring up inverses?
It's up to you.
All right, so I'm gonna do it this way. Because I want 5 to the t to be 5 to the 8 mod 16, it's enough for 5 to the t to be 1 mod 16. If I multiply by 1, I definitely preserve the number. And if you know inverses, then these two statements are actually, oh, did I have a LaTeX typo? We're doing it live. If I want to get back to 065 mod 16, also, this should be 5 to the 4, I'm sorry. This is not an 8. Yeah, okay. Then all I need is 5 to the t to be 1 mod 16. And claim if 4 divides t, then 16 divides 5 to the t minus 1. And if you want to see why, well, if I have a difference of fourth powers, I can just factor it. So 5 to the t minus 1 is equal to 5 to the t halves minus 1, 5 to the t halves plus 1. And then t is divisible by 4, so that first thing is still a difference of squares. So t to the 4 minus 1, t to the 4 plus 1, and then 5t over 2 plus 1.
Yeah. So
okay,
if students are not too familiar with this, they can even do this. Is like 20. If 5 squared is 25, mod 16 is 9, and the 9 squared is 81, which is 1, right? So they know if 4 divides t, you're okay.
Oh, yeah, I guess the numbers are small enough you can just do it that way. Yeah, so more simply, 5 to the 4 minus 1. I mean, I guess this number is small enough I can just compute it. It's 624. So 624 is indeed divisible by... Oh, did I mess up? Do I not have enough factors?
So every 4 you will have 0, 6, 20, 625, right? Every
39.
4.
Yeah, that should be fine. So what that means is if I was going to calculate this, the next few things, 5 to the 16 will be something, and I probably am not fast enough to get it all in one go, but you'll find that it always ends in the 0, 6, 2, 5. 0, and then in black, I'll draw the 6, 2, 5 now. Oh no, that's the wrong blue. Here, there we go. So what that means is by looking at the last 4 digits, I can have a reliable way that I can try to generate a single 0. And you're like, okay, that's great. How can I generate more zeros? And the idea is, well, we got that 0 because when we looked here, we had a 4-digit block at 5 to the 4. If I go a little later, let's say I go to 5 to the 7, you can try to, I'll actually do this in reds. No, I'll do it in green. Imagine maybe I can get this guy as a block, 5 to the 7. So maybe if I go far enough along here, I'll start seeing the last 7 digits are always 0, 0, 7, 8, 1, 2, 5. And the idea is, okay, well, what do I want? Again, I want some large period t such that if I take 5 to the t plus 7, it'll be congruent to 5 to the 7 mod 10 to the 7. And again, by Chinese remainder theorem, all I need is for it to be, it will always be 0 mod 5 to the 7, because I keep throwing on factors of 5. So all I need is for it to be stable mod 2 to the 7. Showing up? Yeah.
It's just barely showing up.
Okay, I'll move it a little bit to the left. Yeah, and again, all I need is 5 to the t is 1 mod 2 to the 7, and then I'll have a large enough period. Okay, well, this is why I sort of did it manually when I had 4, even though 5 to the 4 is small enough that I can just, throw something at it. Here, the number that I'll need is, I think, 32. Because if I have 5 to the 32 minus 1, they'll factor as this big difference as squares, 5 minus 1, 5 plus 1, 5 squared plus 1, 5 cubed plus 1, 5 to the 4 plus 1. And yeah, if you count, oh, what am I writing? No, that's not right, that's not right, ignore that. That's off by a lot of orders of magnitude.
Yes.
All right, 5, 4, 5, 60 plus 1, there you go.
Okay.
Yeah, and now you can count, again, we have enough factors of 2, because in this guy, I have a factor of 4, you have a factor of 2 from here, everything else is even. So that's your 7 factors of 2. And that means if I went and, kind of computed more powers of 5, when I get all the way down, you get 5 to the 39. 39 will also end in 0, 0, 7, 8, 1, 2, 5. Okay, so now you have 2 zeros. And for the JMO problem, what's my goal? I want to get 6 consecutive zeros. So what you can see is almost for any number I pick, if I pick a small power of 5, it will have some trailing zeros in order to pad it to the same length. For example, in the 5 to the 7 row, I padded it to length 7, and then I was good to go. So as long as I can find a single number for which I need to pad 6 leading zeros, then I'll be okay. And if you kind of check the official solutions, so I see a question, why is it 7 in the Q&A? The answer is it can literally be any number. I can repeat this argument if I wanted with, say, 5 to the 6, and you could get 0, 1, 5, 65 to end up later on in the sequence. So the particular number that I pick as my initial number to try to propagate later doesn't matter. You'll find all of the digits keep propagating. For example, like the simplest example is the 5 at the end. 5 keep at the end is there the whole time. The 25 is there the whole time. 125 keeps showing up every so often. But 065 is the first one that has a 0 because it's small relative to its power of 10. So that means if I want to do this problem, I just need one single number for which I can get 6 leading zeros. And for concreteness, I'll just tell you what that number is. If you take 5 to the 20, that number will have 6 leading zeros, 1, 2, 3, 4, 5, 6, followed by some random string of digits. And for concreteness, I'll even tell you what those digits are. 9, 5, 3, 6, 7, 4, 3, 1, 6, 4, 0, 65.
It's a little hidden.
Your number is being covered up by something.
You move it a little bit.
Yeah, there we go.
Bask in the glory of that really large example.
And
wait, Evan, so 6 zeros, you mean you have 20 digits and first 6 are zeros?
Yeah, so the point is this monstrosity with the 9s is a 14-digit number.
Okay.
And in fact, you might notice that it's a pretty close call. Why is it a pretty close call? Because what I'm actually looking at is I'm looking at the ratio of, if I did this with a general n, I'm looking at the ratio of 5 to the n over 10 to the n, which is 1 over 2 to the n. So the reason I picked this particular number is if you take 1 over 2 to the 20, you might know that 2 to the 10 is very close to a power of 10. 2 to the 10 is 1024. That's almost 1,000. So I sort of contrived these numbers so that this 1024 is very close, and so I'll get a pretty good thing here. I'll get just barely 6 zeros if I took this thing to be a multiple of 10. So that's sort of how I picked a particular constant for this number. And it had the nice coincidence that if you figure out what the smallest thing is, you'll get that the value of n that works is n is 20 plus 2 to the 18, which is whatever it is. And it's like, it'll be some 5-digit number on the order of 10 to the 6. So that's how the upper bound 10 to the 6 here is chosen. I picked this 1,000 first, and then I picked this 10 to the 6 to sort of match the 6 consecutive zeros. And so now it looks like a lot of those silly pigeonhole problems, but it's basically a coincidence, I think, that the 1 million appears twice.
I can tell you some comments from my experience of teaching this problem.
Mm-hmm.
I know lots of students see this solution, they agree, they understand. When you ask them to solve this problem again in a month, they cannot do it.
Yeah,
it's true.
Mm-hmm.
So if you guys understand Evan's argument for 5 to the 7 and 2 to the 7, and how he decomposed 5 to 32 minus 1, what's the reason for that, you should do the same steps on your own closed notebook for 5 to the 20. Because only if you solve this problem on your own, you know you can do it again later.
Yeah, that's part of why in the presentation I was so explicit about all the numbers. Like I did the small examples with 5 to the 4 and 5 to the 7 very explicitly, so you can actually see the 0078125, and you can actually see the 5 to the 32 minus 1 factor completely, because it looks easy until you try to do it.
Evan, should it be 2 to the 19th?
I think 2 to the 18 is good enough. So
2 to 18 works because it's 1 mod 4. 5 is 1 mod 4.
It's it's a thing where if you apply phi, I agree it's 2 to the 19, but you get an extra factor of 2 from the 5 minus 1.
Right? Yeah, 2 to the
yeah.
would be good.
Yeah.
Yeah. Also, I guess like just in general, you don't really need to know the exact upper bound. You know that, like, for example, 5 to the t is 1 mod 2 to 7. You know that that's gonna happen like at latest at t equal 2 to the 7. But you also like can improve this by noticing like all the numbers are odd. So like it's not gonna, it's like gonna cycle like at the most like at least 1 2 to the 7. So like you don't quite need to know like whatever Fermat's little theorem is, but like
yeah, it will repeat. Yeah,
it will repeat.
Yeah. So there's a couple of stories I can tell about this problem. One is the way that the way I came up with it is I remember I was in my dorm and I was lying on my bed, and I don't know why, but I was multiplying powers of 5. And when I got to this 390625, about 20 seconds later, I had the idea of the problem. I was just like, wait, I can get the 0 to just appear wherever I want. I can do this with any power of 5. So yeah, I'm not sure what that says about me, but that happened. As for how this problem actually ended up on the JMO, I think Zooming might know more than I do. All I remember is that I got an email saying that they needed like a simple but trivial number theory or something like that. And I sent this in saying that it was simple but not trivial. And they took it anyways. So that worked out pretty well for me. Yeah, the last one thing I want to bring up is that the idea of this problem you can find in other places too. After this problem was selected and made the test and all, I was told that apparently on the IMO shortlist of 1976, there was a very similar problem that appeared, and it says prove that 5 to the n has 1976 consecutive zeros in its decimal representation for some n. So it's the same problem, but there isn't an explicit bound on n anymore. But the 1976 is a lot larger than 6.
Yeah.
And obviously you can do this problem the same way here, and you'll get an n that's on the order of like 2 to the 19 whatever. But if you remove the explicit bound on n, there's another approach that becomes possible. And the idea is, rather than try to look for zeros close to the end, which is what we've been doing, you can try to imagine looking for zeros close to the start. Which is that if, let's say, 5 to the n is very close to a power of 10, then you might expect that 5 to the n, when you read its decimal representation, will say 1, 0, 0, 0, 0, 0, 0, and then actually then there's some fuzz at the end. So what do I mean by close? What I mean is I want 5 to the n to be between 10 to the 6 and then 1 plus epsilon times, sorry, not 10 to the 6, 10 to some power, where I guess epsilon in this case is like 1 over 10 to the 1976. But the point is some very small number. And, well, how can I get that to happen? What you can do is I can take the log of both sides. Let's say log 10. So we will be engineers today.
Yeah, this becomes those pigeonhole problem you will wrap around, right?
Yeah. So this happens, and then I'll take, well, you can even do it this way. I'm going to just divide out by k. And so now I get 1 plus epsilon here and 1. And let me divide. Yeah, the log.
Oh, okay.
Yeah.
So you can do it pigeonhole, but you don't even need that. You can just say, if I have two different real numbers, there's a rational number between them. With denominator not, some denominator. And when I take this n and k, you'll recover some n for which 5 to the n is very close to a power of 10. So that will also be good enough. Now, the question I've had, and I never got around to answering, but I'm going to pose it here, is if you use this sort of method, about how big is n going to be? And I don't think it'll be good enough to clear the JMO problem if you adopt a method like this, but I'm not sure. I haven't tried it yet.
I think for that problem, it depends on something about the 5, right? Because I can always like start with a number that's like a bunch of 9s at the start. And then no matter how many, I have to take it to a really large power to like get it to like become one bunch of zeros instead.
Right.
But that's
So
somehow hard to find an explicit bound. It has to rely on the fact that you know something about log base 10 of 5.
Sure.
You might be able to do some Dirichlet approximation type stuff, but I'm not positive about that.
Yeah, I mean, I haven't thought about it either, but I'm throwing it out here because in principle, you should be able to get zeros close to the head, but I don't know how likely it is. Heuristically, there is a reason to believe that it shouldn't be too far from the bound in some sense, because if you imagine the first few digits are, say, random, which they aren't, but like you can imagine for large n, maybe it starts looking random, then you want you want 6 particular digits to be 0. I guess here I had it start with 1, but I could equally have it start with 2, 0, 0, 0, 0, 0, 0. So in some sense, if it's actually random, I have a 10 to the 6th chance that the first 6 digits will actually all be all 0. I don't know if that heuristic holds up at all, but I'd be curious whether my gut feeling is that the smallest n for which you get zeros in the 2nd through 7th digit is probably larger than 10 to the 6th, but I don't think it should be a lot larger. But again, I don't know.
Yeah, I like your new approach connecting to this, because now the problem suddenly looks very different now, right? It becomes a completely different idea about this problem. Very good, very cool.
I think I tried this approach, Evan, when I first saw it, because the only thing I knew Dirichlet. So if you look at that line with k less than n log base 10 of 5 less than 1 plus 1 over that 10, in your case will be what, 10 to the 6?
Yes.
Times k, right? So the length of this interval is how long? It is 1 over 10 to the 6.
Yeah.
And what do? You generate log base 10 of 5, 2 log base 10 of 5. So you need at least a million such numbers to get to. So their difference is very tiny.
I see. The difference will be around. So we're lucky that log 10.5 is less than 1. I don't know how big is log 10.5. Or 1 over log 5.
0.7 approximately.
0.7. Okay. So the length of the interval will be. Okay. Let's see. So if
you're not doing a real like Dirichlet, right? Because Evan, in your board, there's a typo on the second to last line, right?
Oh no.
Your board,
okay. What did I do?
But you didn't change the multiplication to addition. So the thing's a bit worse than Dirichlet.
Oh, I see. Sorry, it's log 10 of 1 plus. Yes, good point.
Yeah.
K plus log 10 of 1 plus epsilon.
Is it
no, the point is there's a k in the denominator on the right hand side, because in the second to last line, the right hand side is k plus log 10 of 1 plus epsilon. So when you divide by k, it's no longer a Dirichlet problem.
Oh, did I? Okay, I really messed up. Okay, you're right. Okay, that's very different then. Oh no. Okay, so all right, let's rewind.
It's a line above that.
Yeah, so this line is wrong too.
Yeah, that's the part.
Oh, I
It should
see.
still be okay though, right? Because in that case, if you just look at the fractional part, it's saying the fractional part of n times log base 10 of 5 is sufficiently small, and you can still Dirichlet that to some extent. Should be okay.
Yeah,
but I don't think the balance might be a little bit different though.
Yeah, but it's a lot scarier, because if you like try to say, oh, that's actually a lot worse.
Yeah,
because
more something about log base 10 of 5, because I can say, what if log base 10 of 5 is actually like 1/4 minus epsilon? It's not, but like if it was,
yeah, but we also expect log 10 of 5 to like not really be close to an integer, right? I guess the thing about 10 to the cubed being about 2 to the 10 might hurt you, because it tells you that it's actually pretty close to a low rational number.
Okay, so why don't we stop at here? And this gives us something to think about for all of us. And then we should move on to our next one. And Ivan, you are going to change the screen, right?
Yeah, so I'll stop my share now.
Yeah. So while he's changing the screen, I can tell you 2 very silly jokes about Evan's question. Because in the beginning, when people are trying to see all the 5 powers of 5, they might think about using induction to prove there's no zeros, right? Because it works for all 7 numbers. So that's right? But then 5 to the 8th, actually that question is related to one of the silliest Amy question I can even think about. You guys are all look at the old Amy problems. Go to 2000 Amy, number 1. That was a really, really silly question. It's about this 5 to
Oh,
the
is that the one that's like something about not containing a zero?
Yeah, that was
Yeah.
really, really one of the all-time silliest, problem you can think about, right? Yeah. So I'm just filling the time. Now we are ready for the last question.
All right. I can read the problem for you guys. So this is a problem. Actually, should I give away the context of the problem or where it appeared?
It's okay. You can just go.
Okay.
I think the
It's
context is
relevant.
pretty. I think the context gives it away.
Oh, okay. Anyway, yeah. So this is come from this problem came from a theme round in particular, but I'll read the problem first. 1 million bucks, i.e., 1 million male deer, are in different cells of a 1,000 by 1,000 grid. The left and right edges of the grid are then glued together, and the top and bottom edges of the grid are glued together. So then the grid forms a donut-shaped torus. Don't worry about the donut. The point is that if you're at the edge, the two opposite ends of the grid, the point is that if you're at the edge of a grid, there's no such thing as an edge. If you move over, you go to the other side of the grid. Yvonne's drawing a little helpful note. So don't worry about the donut part. Furthermore, some of the bucks are honest bucks who always tell the truth, and the remaining bucks are dishonest bucks who never tell the truth. Each of the million bucks claims that at most one of my neighboring bucks is an honest buck. A pair of neighboring bucks is said to be a buckaroo if exactly one of them is an honest buck. What is the minimum possible number of buckaroos in the pairs in this grid? So that's a mouthful. So the context is the fact that like I have enjoyed writing problems with puns in them for a while. In particular, when I was a senior at Exeter, we host a competition called EMTC for middle schoolers, and I was the tournament director / like head of problems then, and I wrote a lot of problems that involved puns about eggs. Lots and lots of egg puns. Eggplants, eggs eater.
Oh no.
Eggs. I forgot the others.
Please stop.
Sunny side up. So I was in charge of coming up with a theme for this theme round, and it was kind of our fault, but we didn't really start until like late September, early October. So I came up with a theme, which is money, and then I had because I could come up with all these amazing money puns. And if you want to read more, there's a bunch of them that are great on the 2018 HMMT theme round, HMNT November theme round, which you guys should check out. I'm very proud of them. Even though they get disrespected by other people. But anyway, so the point is that there are 2 puns here involving honest bucks and 1 million bucks. So back to the content of the problem, I'm going to share my screen. There's a lot to go through, so I'll help go through that. Let me see. Okay. You should be able to see my screen now.
Okay, wait, James. Let us understand the problem.
Yeah, so I'm going to just kind of explain a little bit. So the point is that you have a grid. This is a large grid. It's obviously not 1,000 by 1,000 here. But the point is that in each cell you have a buck. And each buck claims this sentence right here. At most, nope, that's not what I want to do. At most, 1 buck of my neighboring bucks is an honest buck. So each cell has 4 neighboring squares because it's a torus. Mm-hmm. So that means even an edge cell like this cell right here has 4 neighbors. The 4 neighbors are in particular this cell, this cell, this cell, and finally this cell over here. We're a little short in time, so I'm going to go a little faster. I know there's...
Wait, James. Yeah.
No rush, James. No rush. Don't worry about it.
All right, okay, sure.
So if an honest buck says this sentence, it means...
Yeah. So we have to interpret what this means, definitely. So if an honest buck says this sentence, then that means that this sentence is true. So if we have an honest buck, let's say the cell over here is occupied by an honest buck, which is red. That means at most one of its neighbors are honest buck, which means we have one of the 2 scenarios. Either all of its neighbors here are not honest, so they're all blue is dishonest here, or they have that one of its neighbors are honest. In which case, let's like if this buck, we have like a neighbor that's honest and like 3 neighbors that are not honest. So that makes enough sense already. And then the converse is that if you have a dishonest book, that means that they must be lying. Like, so they must have at least 2 neighbors that are honest books. I'm not going to draw it out, but there's like a lot of cases that can happen here. Basically, if you're a dishonest book, you're required to be surrounded by 2 honest books, and there's 11 different configurations in which that can happen. So there's a lot. I won't draw them all out.
Okay,
so now,
wait, James. Wait, James.
Yeah.
And we want to find the minimum possible pairs of red, blue.
Yes. So you basically want to find the minimum number of red-blue pairs. So this problem is interesting. So it's really hard to get a grasp on this originally, but the point is that if you really understand this problem, is that for a given red cell, it must be surrounded by a bunch of blue cells, and then if you're a blue cell, you must be surrounded by a bunch of red cells. So that's why the statement actually has like value. It's because you're asking for the minimum number of red-blue pairs. The condition itself already tells you there's going to be a lot of red cells that are next to blue cells and blue cells that are next to red cells. So now you have to figure out how to get a handle on this statement as a whole. So I'm going to focus on the honest buck portion, which is just the 2 configurations here. Just mostly because from the dishonest buck perspective, it's really hard to get a handle on. So you have one of these 2 cases. You're either an honest cell, an honest buck right here, this red one right here, and then you're surrounded by 4 blue cells, or you're an honest buck and you're surrounded by 1 other honest buck and 3 blue cells. But then, like, how do you like get a grip on this situation? If you look at this situation from the perspective of this higher red cell, you must also touch at most 1 red cell. So that means that these 3 that are also touching you over here are also all blue. Does that make sense?
Mm-hmm. So the first case, when you're surrounded with blue cells, when the red does not give you minimum, right?
Yeah.
So it's much better to use as much as you can the second case.
Yeah, so that's a good intuition, although we are going to try to be a little more rigorous about this, or even like, but always having the kind of intuition is good. Just because like, I need to begin writing solving a problem proof-wise, even though it's a short answer problem, you want to be able to solve this, like be able to prove your answer. You always want to have the right intuition. So now these are kind of basically, it's nice that in the second case, we kind of close it off and figure out how the other remaining cells must happen. So now how do we think about these 2 cases? Well, the nice thing is that now in the red cells, they're kind of closed off in both cases. So if we can think about this problem in terms of something called like connected components. So if we just look at the red cells, basically they must come in either blocks of 1 or 2, and they must be surrounded by blue cells, right? So that means when we color this entire big, large grid, we're going to need a bunch of cells that are either 1 or 2 red cells. And then furthermore, these gaps can't be too far apart because each blue cell must touch at least 2 red cells in particular. So it's going to be really hard to visualize because like you can have a bunch of the 2s and the 1s combining into some weird like aperiodic pattern that covers the entire grid. But we have to keep in perspective our statement, which is we want to minimize the number of red-blue pairs. So I think what Yvonne says here is really valuable because in the first case that we have, also sorry, I'm not really able to look at the Q&A. So if anyone has questions, one of the other panelists should tell me. So in this case, you have a bunch of red-blue pairs that out of the 4 possible pairs that are connected here, these are all red and blue. It's kind of not great. In this case, you have a bunch of red-blue pairs too, but you also have some same color pairs, which is a lot better. So we want to try to kind of prove the second case. That we want to prove that like we mostly want to color with the second case here. How do we get a handle on this? Do you guys have any thoughts in the other panelists?
I'll say that when I tried working on this problem and I unfortunately wasn't able to solve it completely, I tried focusing on like there are 3 types of pairs: honest pairs, honest dishonest pairs, and dishonest pairs. Mm-hmm. And it's possible to find some relationships between them, but only one of the equations you get, only one of the inequalities ends up yielding anything useful. The other inequality, any other because there's so many different possible configurations, it's really difficult to do anything non-trivial with that.
Yeah.
So there goes 2 hours of my time.
Oh, that was 2 hours. Okay, so this appeared on a November test. So the thing is, the problem with this is that I wrote it, so I never actually solved it myself. So for me, the solution was immediate, unfortunately. I think maybe not that many people test solved it.
I remember test solving it. Right.
Oh, Yannick is a legend. So.
No, I didn't get the right answer. I don't think I got the right answer.
You did?
I don't think I did.
Oh, so this is
I may be onto something, but like I don't think I got it.
Okay.
It's very easy to come up with like equality cases that aren't actually equality cases.
So that's what makes this problem tricky. Actually, when I originally was trying to create this problem, I created a bunch of versions I think that were not that great because the problem is that they're very easy to guess. They're not. It's hard to come up with problems because there are two. All these problems, there are two types of problems. There's one in creating the bound, and then you have to come up with the construction. It's really hard to create a problem that has an interesting, like, problem to solve, but that isn't just trivialized by just guessing the construction, right?
Yeah.
So actually,
it's not a numerical answer contest, right?
Yeah.
You cannot require them to write it.
So I'm gonna just simplify things that David brought up, and I'm gonna only have two variables. The two variables are gonna be K and B. B is the number of pairs, buckaroo pairs. So red-blue pairs. This is the number of red-blue pairs. I'll denote it here. Red, blue. And then K is just the number of red cells itself, the number of honest bucks. So K is the number of red bucks. So it's a little
ratio.
Yeah, so it's nice to have only two variables. The problem with David mentioned three variables, but you need more equations, and that could get a little messier. So I only need two, or more inequalities. So in this case, I'm only going to need two inequalities, and I can kind of come up with some bounds that I like. So the first relationship between K and B here is just from the perspective of the red cells. Can we get so the thing is that for each red-blue pair, the thing to notice is that exactly one cell is red, which seems like a really dumb statement, but that means that we can count we can get a bound on B by focusing on the red cells, and we can also get a bound on B by focusing on the blue cells. So focus on the red cells. So this one has one cell here. It contributes 4 red-blue pairs, right? And then this, the second part has 2 red cells and contributes 6 red-blue pairs. And because all the red components because we have separate connected components, we're going to look at each red component separately and just get these bounds. So for one of them, we have, so then it follows that here that K, our first equation is going to be that K is, I think, sorry, let me get this correct. It's 3K is at most most B, right? Is this correct?
Yes.
Okay, 3K
because you want B to have a lower bound.
Well, this is so I don't really care the bound right now yet because the problem with K is that K can vary between 0 and 1,000,000 as of right now. Obviously, it can't because there's going to be some bounds because you need some red and some blue, but we don't know what K is yet.
Right.
So I'm just saying that this is the bound that we get from considering the red cells, right? Because either we have K equals 1, K equals 1, KB. Either we have K equals 1 and B equals 4, or we have K equals 2 and B equals 6, right? These are just in the counting the number of pairs.
Mm-hmm. You don't even need to worry about components.
So it's adding a bunch of things together. Or, yeah, you don't even need components. Basically, for each red cell, we have at least 3 blue cells next to it, right? I guess that's what matters. You don't even need to consider components. This just says that each red cell has at least 3 blue cells next to it.
Okay. Wait, James. We should finish soon, so we have 2 options. We either finish in the next 5 minutes, or you leave the audience an interesting question, and we continue next time.
Yeah. So actually, the equation right here doesn't actually depend on connected components. Just looking at the red cells, they must have at least 3 blue cells next to it, right? Then I'll kind of leave you guys to think about it for next time. But you can also look at this from the perspective of the blue cells, right? And then see what kind of equation you get from that. And then see kind of how you can algebraically manipulate things so that you can get a minimum bound on the buckaroo pairs.
I think the construction is the hard part.
Yeah, I think the construction is hard.
So once you come up with the values of K and B that are required, then the construction falls. Just like,
really?
Yeah.
No, I came up with the bound. I don't think I got construction, so I put down a worse answer.
Well, so once you come up with a second inequality, I think the second inequality will give you a bound that no longer depends on K that you can get on B. So they get a minimum value of B that does not depend on K.
Yeah.
That will give you, and then that will give you a K that must satisfy for that bound to hold. And by looking at the equality cases of the two inequalities, you can definitely do the construction. I'll leave it at that for now. We can probably just talk about the rest of it next time once people have thought about it a little more. But yeah, so that's the problem that I wrote for the theme round. I thought it was really cool. Especially if you guys solve the rest of the problem, you guys will probably think it's cool too. I've always wanted to create a knights this is like inspired by a bunch of knights and knaves problems. I think on like HMT I've seen like liar kind of problems. I was really inspired because on my very first HMT I did very well in the combinatoric section, and that's because I got harder knights and knaves problems kind of correct. So close to my heart. It's inspired also by a 2012 Lexington math tournament problem. I think one of the theme problems, number 9, involved knights on knaves on a grid. So I'm like, I'll put a bunch of lying deer on a grid and see what happens. Yeah, and then once you guys solve this problem, I definitely encourage you guys to kind of think about maybe you can think more about the actual like characterizing of the grids, and maybe you can come up with your own problem that's based on this. Because the question I asked is not necessarily very natural. The buckaroo pairs. Maybe there's another interesting question that you can ask about the configuration.
Buckaroo pairs is like fair. I'm not going to claim it's like supernatural, but it's very easy to get lots of buckaroo pairs by doing a diagonal tiling. Like, because if you have if you color like red, blue, red, blue, red, blue, red, blue, then I believe that's a valid coloring, and then every pair is a buckaroo pair.
Right. Red, blue, red, blue.
If you do a checkerboard coloring, I think that works. I'm not sure if that quite works.
So the thing I'm curious about, I haven't solved the problem yet because I just saw it. Although I don't feel like I'm close either. Why did you not just ask for the minimum number of honest bucks?
That is a different configuration that I believe is a lot easier to find.
Oh, is it different? So your inequalities won't actually be. Oh, I see. Okay.
So all the inequalities will be different depending on what the question you ask, what you're solving for. So there is actually so the interesting thing is there is a bound on K. I don't remember what it is because I wrote this problem 2 years ago. There is a bound on K that you can find. I think there's an upper and a lower bound you can find.
But they're both different.
But they're both different from this inequality case.
Okay.
Yeah. So you don't actually need to find those bounds at all to solve this problem. So actually, I think the connected components part I mentioned does not actually relevant for this problem. But
I see. Okay.
This is how I thought about it originally.
Wonderful. Yeah. I think we are going to stop here because this is a wonderful question. I just feel bad it's become a numerical answer question because the question itself is so good for asking for the proofs, right? So I think
quite fair. I don't think it's much easier
to really prove this thing, right?
Okay. I don't think it's much easier though.
Yeah. Okay, so we are going to stop at here. So thank you everyone and good night.